Welcome to this first lecture in the Serverless Machine Learning course. In this lecture, we're going to go through feature engineering, pipelines for machine learning, how we orchestrate or execute those pipelines. It's all going to be Python. And we're going to look at the output of the pipelines, the features, how we can store them in a feature store, and we're going to go through a prediction service. You're going to build your first prediction service after this lecture in the first lab. And the first prediction service is based on the iris flower dataset, a very well-known dataset for machine learning. We're going to build a UI with GitHub pages. We're going to have a pipeline orchestrated in GitHub Actions, and we're going to store the features in the Hopsworks feature store. And finally, we're even going to include some analytics of your model, so monitoring of the performance of your model. So do the lectures, do the lab. Good luck. In today's lecture, you're going to build your first serverless machine learning system. It's going to be a prediction service based on the well-known iris flower dataset. It's going to be a very simple service. Once per day, it's going to generate a new flower from the iris dataset. So synthetically, we're going to create a new instance of a flower. And we're going to have a model that's going to predict what type of iris flower it is. And we're going to publish in a user interface based on GitHub pages the flower that was predicted, the actual flower that was there, and we're going to show some statistics of the accuracy of that model over time. So it's a very simple predictive service that we're going to build based on the iris flower dataset. If we look at some of the other things that we're going to need here, we're going to have Python programs that create the features for the iris flower dataset. We're going to store the prediction logs because we're going to do some analysis of the features. We're going to train the model as well. And we need to orchestrate the execution of our Python program. So we're going to use this platform called GitHub Actions for this. We're going to store the features and the models in a platform called Hopsworks.ai. So if we look through the different parts of this system as we set it up, what we can basically say is that we have compute here on the left-hand side. So the compute for creating the features and for making the predictions are Python programs orchestrated by GitHub Actions. And they'll need to run at a certain frequency or cadence, so once a day. But the training of models, we don't need to do it once a day necessarily. You typically would train a model when you need to train a new model because maybe your model is decayed. And you can do that from a notebook, a Colab notebook or Jupyter. And this is the compute that we'll have in this serverless system. Now the state that will be stored will be the features, the data for our machine learning model, the actual model itself, and we're also going to store the prediction logs in Hopsworks.ai. And then finally, the user interface to our platform will be based on GitHub pages. And GitHub pages is part of GitHub, and every GitHub repo you can have a GitHub pages UI, and we're going to create one of those in very simple markdown code. Now we're going to work primarily with tabular data in this course. Tabular data are tables of data, and we're going to train our machine learning models with the data in these tables. We're going to make predictions with the data in these tables. And tabular data is pretty much everywhere in the enterprise. So if you think about databases, data warehouses, data lakes, and even files that you find in Parquet file format, they store what we call tabular data. And if we look at it down here, we can see that we have tabular data in the form of this green table here containing 3 columns, a credit card number, an amount, and a location. We have a column. We have an individual row here. We've got 3 values in the row, the credit card number, the amount, and the location. We have a primary key. In fact, this primary key should be unique for every row, but the credit card number is not unique for each row, as you may tell here. So you would need to add an additional timestamp here to make the primary key. So it would be the credit card number and the timestamp. And then we have an individual value within a given row. So for the location value, we can see within this row, we have the word Stockholm. So this is the terminology we use in databases. For your curiosity, Sebastian Raschke, who's a well-known author in machine learning and Python, his educated guess is that the tabular market, the market for machine learning with tabular data, that's much of the data in the enterprise, is probably larger than the market for machine learning, doing all the self-driving cars and medical imaging and you know, video analysis that's out there, which in turn is probably larger than the market for natural language processing. So things like translation and so on. So tabular data is very important, and it's widely used within the enterprise, and lots of prediction services are being built on tabular data. If we look at this particular example here, we've got credit card numbers, amounts, and locations, and we're going to see also that extend these you know, these columns to add in fraud for credit card prediction. That would be a well-known problem that you would like machine learning to solve using tabular data. Now, if you look at the terminology we have for tabular data here, we have the term table, but we also have, you can see in parentheses, the word feature group. So in this course, we're going to use some of the terminology from what we call feature stores, and feature stores store these features in tables. And in the feature store terminology, we use the word feature group to represent a table. A column will be referred to as a feature. A row will be referred to sometimes as a vector, and sometimes you'll refer to part of a vector. So you might say, well, just the features on this row, so that would be the feature vector. Primary keys sometimes we'll refer to as entity IDs, and then the actual data inside a given square in this table we'll call a feature value rather than just a data value. But remember, it's basically the same, mapping one-to-one to the database concepts if you've taken a course in databases before. Now, we're going to work primarily with supervised machine learning in this course as well. So by supervised machine learning, we mean that, you know, there's going to be some label on the data that we're training with. So we're going to have the input features, and in this case, we look at the input features. We have the amount, and we have the location. Go back here. See. So we have this amount, and we have the location, and these should be able to help us predict if a given credit card transaction is fraudulent or not. Now, probably there's not enough information in here to help us predict. Like if we looked at the data and analyzed it, what we could see is that our first credit card transaction here happens at 8:44 a.m. on the 1st of January in Sao Paulo, and that's okay. It's not fraud. At 7:44 p.m. in the evening at Rio de Janeiro, that's okay. But only 1 hour later, the next credit card transaction took place in Stockholm. So that's indicative of fraud. And then we'd hope that the system would learn that the next transaction after that is probably also fraud. So, you know, if we're to train a machine learning model with supervised machine learning algorithms to predict fraud using data such as this one, we'll need to have input features, we'll need to have the label column. In this case, we can also see that we have an event time column and an entity key or primary key. So in this case, you can see that we're not using the term primary key, as we saw in the last slide, that the credit card number was not unique. The entity key here is basically in combination with the event time is unique, and that's our primary key over this whole table. And that's the kind of terminology we'll use in the feature store space. So we have, for the same entity key, we have many observations of different rows, so different events that have happened, and we have the label as well for those. Sometimes you'll have a different table which won't have the label, but we'll be able to join together those features with other features in a table that has a label, and that way we'll be able to create tables of features and labels that we can use to train our machine learning models with. Now, if we take, we said before that the row we often refer to as a vector. What we use more commonly in this course is the term feature vector. So feature vector is only those columns that are features that we're going to feed and pass into the model, both for training and for serving. So an individual row will be a feature vector. So for example, if I'm trying, in this case of fraud prediction for credit cards, if I'm trying to, in real time, take a given credit card transaction, so let's imagine it's the last credit card transaction, and in real time I'm trying to predict if this particular transaction is suspected of fraud or not, what I'll need to do is retrieve this feature vector, the features for just this particular row, and then pass them into the model, make the prediction, and then say if it's suspected of fraud or not. We'll see that when I say retrieve the feature vector, we're going to use a platform called a feature store to store pre-computed features for us. And And we'll see that that's part of this notion of what we call real-time machine learning that we'll get into much later in the course, really towards the last lecture. Now, in supervised machine learning with tabular data, the very simple way to think about how we store our feature vectors and our labels is in this tabular format. Another simple way to think about it is that really machine learning with tabular data involves taking a train function, what we'll call a train pipeline, and passing it in features and labels, and the output of this training pipeline will be what we call a model. And the model is obviously the abstraction or the approximated function that we're going to use to make predictions with. So when we have a model, we can take another one of these feature vectors, pass it into the model, and it'll give us back a prediction. And that's basically another pipeline we'll call the inference pipeline that we'll look at in this lecture. Now, to get us started on our journey in building this first prediction service, if you haven't used Pandas before, we're going to go through a quick introduction to Pandas. This is not a substitute for learning Pandas completely by itself. You should really read a book on Pandas, do some programming in Pandas. We have an example introductory notebook for Pandas on the course GitHub repo. But basically, we'll have a look at some of the features in Pandas that we can use to create features for our models. Now, Pandas represents data as what we call data frames. It looks like a table that we had on the previous two slides. It's the same table that we had from before, but the terminology we use in Pandas is slightly different. So we have rows, the same as before. The columns we'll call series, and each column will have a data type. So we call it a DType or data type in Pandas. So the fraud data type here you can see is of type Boolean. The location and the amount columns have different types. So the location is a string, and in Pandas a string is called an object type, and then the amount is a floating point number. I mean, the $sign is just used here for visual presentation purposes. The value is stored internally as a float. And then the credit card number is a string as well, an object, and then the event time we store as a date time object in this case. So these are the column types, or in Pandas we call column series, and we're going to manipulate this Pandas DataFrames with Python code. So it's going to be simple Python program, and let's look at a very, very simple example here. So we're going to start with a dict in Python, and this dict contains the same data that we saw on the previous slide. It has the credit card number as a column, and then it has 4 different values, so 4 values in that column. We also have the trans date time column, the amount column, the location column, and the fraud column, and all of the values for those columns are defined here in this Python dict. So this Python dict will contain the data that we need to create this data frame from. And we can create the data frame with this PD object. So we import Pandas. This is a convention that you'll see in code. Import your Pandas library as PD. And with the PD object, we can call pd.dataframe to create a data frame with our dict using the .from method. So when we call df after we've created the data frame, it's going to basically show some sample rows which have been emitted here. But another thing that's very important to do, or very useful to do when you get started, is to call info in your data frame to see the types of the different columns or series in your data frame. Now, one thing we can notice is that yes, we have our 5 different columns from credit card number to fraud. The types look okay, but we notice that the object type has been interpreted for the trans_date time column. Now, we said on the previous slide it should really be a date time data type in Panda, because that's what we would expect to have for this event time column, or the trans date time column, trans_date time column. So how do we change this column type, or cast this column from a string to a date time? Well, you can do it as follows. You can basically refer to columns within your Pandas data frame by using this syntax here. We have the square brackets, the name of the column, and this says apply this for this particular column. We're going to save in here, and then we're going to use Pandas to cast the column type, the series, from object, which is in here, to date time. So it's going to take all of the rows all of the entries in the trans date time column, and it's going to cast them to date time, and it's going to save them back in the original trans_date time column. So if we print out the result of this, we can see that all that has happened in this Pandas data frame is that we've cast the trans datetime column from string to datetime 64. And that's great. And you're going to do this quite a lot when you're working with Pandas. You know, the data frame data types that you work with will help you, you know, to perform operations if it's a numerical column or if it's a string column. So it's important to be able to work with the primitive data types supported by Pandas and the operations that they support. When we have the data in our data frames and we want to process that data, in a traditional programming language, you might consider using loops, a for loop or a while loop, to process the individual rows, but that's extremely inefficient in Pandas. What we typically do is instead we define a Python function, and that Python function we're going to call a user-defined function. So this Python function that we can see here on the screen is called isSmall, and this particular function it takes as a parameter a row, and what it does is within that row it extracts the amount column and it returns whether that value is less than 100 or not. So this isSmall function we can actually apply to our data frame using the next line. We can see DataFrame.apply, and for each row in the data frame it's going to apply the isSmall function, and it's going to store the result in this column called is_small. And this is a new column in our data frame. So when we return df here, it's going to call df.head, and we'll see the following. We'll see that this column is created, isSmall. And if we go through it row by row, we can see the first row it says, is the amount less than 100? And the answer is no, so we get a false. And then we get 12 is less than 100, that's true. 866 is less than 100, that's true. And 112 is not less than 100, so we have false. Now this is you know, a more verbose way of writing what we could have written with what we call a Lambda function applied to an individual series or column. So we could say, instead of applying to the whole data frame, just apply to the amount column, and we applying a Lambda function. So we're defining this function inline. So it's an inline function, a Lambda function. And we can see that the amount here is greater than 100. We're going to return true. So in this case, the result is stored in the isBig column. So you can see in the first row we have 142 is greater than 100, 12 is not greater than 100, 868 is not greater than 100, and 112 is greater than 100. So apply and Lambda are good ways to use Pandas to apply functions to process the data in your Pandas data frames. So one of the problems of the apply function in Pandas and UDFs is that it's not particularly efficient compared to implementing operations with what we call vectorized operations. If you have small volumes of data, maybe megabytes in size, you mightn't really worry too much about this because it's not going to affect the overall time it takes to process your data. But as your data volumes grow in size to gigabytes in size, you can get huge speedups by using vectorized operations instead of UDFs and apply. So in this example we can see below, with 100,000 rows, we're getting a 50 times speed up by moving from apply to a vectorized implementation. So if we look here, we can see that we're just basically computing the square of a number x that's in the column A in data frame 2. So we have data frame 2, column A, where we're computing the square of that number. And this is done with an apply and a Lambda function. So it's a UDF, our Lambda function, and then we're applying it to every row. We can see that this takes, on average, 3.42 milliseconds per row, or per loop. It's going to take only 59 microseconds in the vectorized implementation, which is basically saying df2, or data frame 2, column A, we're going to get the square of it by calling **2, which is the square operator in for Pandas. Now Pandas also provides support for what we call exploratory data analysis, or EDA. So EDA is one of the first steps you should do when you're trying to create features with frameworks like Pandas. You want to look at the data, you want to understand your data, and that means inspecting the data. So we can use the head command we can see on your data frame here. So we've got a data frame df, and if we call head on it, it'll return the first few rows. So we saw that on some of the earlier slides where we saw some of the data in the data frames. We just called df at the end of our cell in our Jupyter notebook, and that's equivalent to calling head, and you'll return the first few rows in that data frame. If you have numerical features inside your data frame, you can call describe. You can call it on individual columns as well, and it will compute the descriptive statistics for that particular column or data frame. That means the mean, the max, the min, the standard deviation. You might also want to know if you have a categorical feature. So it could be, for example, a country that the user is based in. So we can have this data frame column called country, and we might want to know what are the countries where the credit card transactions were performed. So we'd call unique on it, and it'll return all the countries where this credit card had been used. Now or all the credit card transactions, I should say, in total have been used. Now for instead of maybe have too many rows are going to be returned because you have a lot of different categorical values, so you just want to know how many values are there. So you can return the number of unique values for a column with n unique, and this is also true for numerical features. We can use it again. Now another thing that's important to do when you're inspecting and understanding your data is understanding if data is missing. So if there's a null value in any of the columns in your data frame, you can figure that out pretty quickly by calling isNull over the entire data frame and then summing up the number of null entries there are in all the columns. So this will return the number of null values for all of the columns in your data frame, a very useful operation. You might also want to know within a given column how many different values there are in that column, and this works with both numerical and categorical features. So for example, in our credit card fraud example, we might call on the fraud column value counts, and it'll say, well, we have 1 million transactions that are not fraud, but we have 1,000 transactions that are suspected of being fraud, and that's what value counts would return for us. Finally, you often want to visually inspect your data frame, and you can do that by plotting it as, for example, a histogram. So in the popular Seaborn visualization library in Python, you can take a Pandas DataFrame or a column in a Pandas DataFrame, and you can plot a histogram for it, calling sns.histplot. So a popular way of computing features is what we call aggregations. These are operations over all of the values for a given column, for example, a series, or for data frames as a whole. So some of the examples of the built-in aggregation functions in Pandas that are quite efficient are count. We can count the number of rows. Often we might want to do this over a period of time, a window of time. So you might want to know, for example, how often a transaction has been performed on a credit card in a 1 hour or 1 day or 1 week period of time. And we'll look at that soon. We might want to know also the first and last rows in the data frame. We want to know the mean value for a given column, or maybe for all of the columns in the data frame, the median value, the min, the max, standard deviation, the variance, the mean absolute deviation, or even compute the product of all the rows for a given column, or for even all columns, and similarly sum up all of the rows in a given column. So we might want to know, for example, the amount of money spent on a credit card for a given credit card number, and we can call df.sum to do that. And you can have things like filters that you can add to these as well to say, well, filter out only for the particular credit card number. Now I mentioned that often when we compute aggregations, we want to compute them over periods of time. In Pandas, we have support for time series operations with what we call a rolling window. Now a rolling window might be, you can see I have a question here, what is the 7-day rolling max or mean amount of the credit card transaction for a given credit card? And often you'll group them by your credit cards by their credit card number, and then you'll compute your aggregations over them. But if we look at this example, we have here, we can see a set of credit card transactions, and you can see them happening over time period. Well, what we like to do is with a rolling window is to say, well, for this 1 day time period here, compute some aggregation over the credit card transactions in that period of time, or a longer window, a 1 week or a 1 month window. So if we, if we have a look at the 1 day period, we can see that with our data frame, we can compute the rolling window over a 1 day period of time. So 1D refers to the time window, 1 day. And then for a given column, the amount column, we can say what was the max amount for a given transaction in that 1 day period of time. And for a week, we can use a different aggregation. Here we're going to use the mean. So what was the for all of the given credit card transactions in that 1 week period, what was the mean value or average value? And then finally for the month, we can say, well, what was the minimum spend of all the transactions within that credit card for that 30-day period of time. Now, to use these time series operations or rolling windows, we do need to set what's called the date time column as an index to the data frame. Now, if you remember earlier, we talked about having a unique identifier for each row in a table, and in database terms, that's called the primary key, which identifies uniquely each row. In feature groups, we call them entity IDs. But in Pandas DataFrames, we call this the index. The index contains the unique identifiers for all of the rows in our Pandas DataFrame. So by default, when you create a data frame in Pandas, there's a hidden index, and it has a unique integer ID for each row. But you can actually set the index to be one of the columns in your data frame. So if you have a date time column in your data frame, which in this case refers to the time at which the credit card transactions are performed, and we do have one, it was the trans_event time, we can set that as the index. And when we set that date time column as the index to the data frame, then Pandas is able to know, okay, I'm going to compute this rolling window over a 1 day period of time because I know the time at which each of these rows were executed or observed. Now, this was just a very brief introduction to Pandas. You should read up more on Pandas if you don't have any experience with Pandas. Here's some links for introduction to Pandas and Colab, working with missing data, visualizations. There's books on Pandas. It's a very large area. We're going to cover quite a lot of it in the course, and you'll learn by doing, of course, and within the course you'll learn by doing. But it's a very useful framework for doing feature engineering in Python. So we'll move on now to look at training machine learning models with the data that we have in DataFrames. It's not going to be a core focus of this particular Serverless ML course, but we'll go through an overview of what you need to know for the course. So we'll start with the features that we looked at earlier, and we're continuing with the credit card example that we had earlier. So fraud is the problem, the machine learning problem that we're trying to solve for credit card transactions. And you can see we've highlighted here in orange the two features in our table, the amount and the location, and then we have our label, which is fraud. But we can see that we've highlighted here the amount and location and called them a numerical feature for the amount, and we've called it a categorical feature for the location. So I've mentioned these already in passing, that you have numerical features and categorical features, but these are what we call feature types. And this is different to the data type. So our amount column is a float, our location column is an object in Pandas or a string, and strings, we typically call them categorical features in machine learning, and floats or ints, we call them numerical features in machine learning. So they're two examples of what we call feature types. You can read up some more in the reference below, but you can also have a taxonomy of feature types. So we're not restricted to just categorical features or numerical features. What we can actually do is we can also have array-based features. So embeddings are popular as a way of representing high-dimensional data, sparse data, and compressing it into a small fixed length number of floating point numbers. You can have lists of features as well, and you really do that for efficiency, just because it's more efficient to process a set of features in a list. Now, if we go over to categorical features, these are things like we gave the example of the country in which the credit card payment is made. Countries don't really have an order in them. You can't say that if you take two countries like Denmark and Djibouti in Africa, that they're somehow related to each other because the letters, both of the countries begin with the letter D. So there's no inherent ordering in countries. They're nominal categorical variables, you would say. Some categorical variables may be have an ordering, an inherent ordering. So, I'll take a bad example, which might be hurricanes. So hurricanes have a, they have a strength between 1 and 5, and you might say, you might take weather. You could take weather's probably a better example because it's not numerical. It's going to be dry today. It's going to be damp. It's going to be wet, or it's going to be very wet. So if those were our different categories, well, we could say there is an inherent ordering. You've got the amount of rain. It's dry. It's damp. It's wet, or it's very wet. We can order those, and we can even compute a mean over them. So we said if we took an example of categorical ordinal variables over a period of time, we could say, what was the average weather type? And you might say, well, for Ireland it was damp. You also have numerical features, so these are going to be floats or numbers. And sometimes, and we'll go back to the hurricane example because that's a good one, because the values are between 1 and 5. So a hurricane can be measured on the Saffir-Simpson scale, so it's between 1 and 5, 1 being a smaller hurricane, 5 being the largest. And you can have that as what we call an interval numerical variable. It's called an interval because there's no zero. So in the hurricane strength scale, there's no zero value. 0 means it's not a hurricane. But you may have other numerical variables or numerical features, and we could take rainfall, for example. There is a 0 for rainfall. So maybe one day you have a rainfall of 10 millimeters, the next day you have 20. You can talk about what, that the rainfall doubled from one day to another because the reference here is 0. So you can say from 0 to 10, we doubled to 20. And that's why it's called a ratio numerical variable. So these are the general feature types that we deal with in machine learning. And this is what we call a taxonomy of them. So you can use this to help you understand the data that you're processing. It's not enough just to have the Pandas data types, whether it's a string or a float or a Boolean. We also need to know it in terms of what type of feature is it. Is it categorical? Is it numerical? Is it an embedding? Because this will help inform us, we'll see later, what type of transformations we may need to do in the data to help improve the performance of our models, or to adapt those particular pieces of data to work as correct input types. Maybe we need a numerical input type for our model, so we need to transform the categorical variable into a numerical variable. But knowing that it's a categorical feature type really helps you to understand what operations you need to perform on that piece of data or feature. Now, another technique that's quite powerful is what we call feature binning or bucketization. So imagine we have some data about customers. We know their date of birth. So we have that information about the customer. We also would like to know their product preferences. So we want to train a model to learn or discover relationships between the customer's date of birth and product preferences. Now, if you have, thousands of customers or even tens of thousands of customers, there's 365 days a year, and then people could be born in different years. So it's what we call very sparse data. The amount of people we will find born on the same day that the model can use to infer relationship between product preferences and when people were born is very hard, right? So what we can do instead is we can take the date of birth and compute the person's age from the date of birth, and that's a reasonable starting point. What we can also do is we can take the age and group them into meaningful ranges here. So we can see 0 to 21 is a meaningful age range, 22 to 39, 40 to 59, and over 60. Or you could have a simple under 21 or over 21. Particularly in the States, if you're talking about the sale of alcohol, for example, you're allowed to buy it when you're over 21 and not when you're under 21. So what we can take is just this raw data, which is the date of birth, and then convert it into the customer's age. And then from the age, we can then say, well, they fall into one of these different, you can see these different bins. So we have 4 bins highlighted here. And we can see basically by just plotting out some data, here we have some data that we took all of the customers who bought products, we've put them in the different bins, and we can quite easily see straight up that most of the customers seem to be in this particular bin, the age 40 to 59. We can see that it looks like there's over 500,000 customers in that range, where we have maybe only less than 100,000 customers in the 0 to 21 age range. So we've already learned something by putting the data into bins and doing some EDA on our data. But in general, numerical variables can be transformed into categorical variables using binning, and this makes it easier for machine learning models sometimes to extract patterns from the data. So you can do it manually. We're using our domain knowledge about the problem to identify what are reasonable bins to use, and then the model will have an easier time of inferring this relationship, in this case between the customer's date of birth and the products that they prefer at this online e-commerce store. Another technique that's been used quite extensively in the past is what we call feature crossing or feature interaction. So feature crossing is when we have the co-occurrence, 2 features happen at the same time, and they're highly correlated with the label or the target we're trying to learn. Now, Feature crossing has gone out of fashion quite a bit recently because deep neural networks are very good at learning feature crossing, and feature crossing, is something that's manual. It requires deep insights in the problem domain. You have to do a lot of testing of feature combinations to get there. There are new frameworks which will help you do it automatically. But the reason why we're introducing feature crossing here is because most of the modeling that we do in tabular data is not neural networks, deep neural networks today. It's in fact, decision trees are very popular. So XGBoost is a very popular framework. And in XGBoost, it's not particularly good at learning feature crossing. So it helps if you can discover the feature crosses yourself. That might be helpful for to provide predictive capabilities to the models that you're going to train. Now, how do you implement a feature cross? If you have numerical features, what you can do is you can basically take, for example, the credit card amount we saw in our fraud example, and let's assume we got another feature from another data set. So we know the air temperature at the time that you paid for this good, this amount on your credit card, and we could basically implement a cross by multiplying the credit card amount, the amount of money you spent, and the temperature. The problem with this is that, of course, it's going to be very sparse. We're going to have lots of different values, and it's going to be hard for your model to extract patterns if we have a state space with millions of potential entries. So what you can do instead is use the binning technique we saw earlier. Maybe we could turn air temperature from cold to mild to hot, and the credit card amount could be from something like low, medium, large. So then we have quite a small state space of potential combinations of credit card amount and air temperature, and then there may be a feature there that can be used to provide some predictive capability to the model that you're trying to train. Now, if you take numerical features, then we can multiply them together with binning, but categorical features, we typically take what we call the Cartesian product of the categories. And we can see that in this example below. We have binned latitude, binned longitude, number of rooms per person. So this is a well-known example for predicting house prices. There's a well-known data set for predicting house prices in San Francisco. And what you can do is you can break down the city into grids. And that's what we call binned latitude and longitude. So different areas of the city can be represented by different latitude bins and longitude bins. And then we can also compute as a categorical variable the average number of rooms per person in that particular bin, in this location in the grid in the city. So here it's 0.6, and maybe you're going to have a ratio from 0.3 to 1.4, or whatever the actual range of average number of rooms per person in the city is. But together, those three features have been shown to be quite good in terms of helping predict house prices in a given area. So this is a useful feature. If you cross the binned latitude, binned longitude, and average number of rooms per person, this helps you solve that problem of predicting house prices in this California or San Francisco housing data set. And I mentioned before, finding good feature crosses is hard. It'll require deep insights to the problem domain. There are libraries that can help you automatically discover some of these feature crosses, and sometimes it may be worth your while to use them. We're not going to go through them in the course, but it's good to know that they exist in case you really need to use this technique to define new features. Now, I mentioned in the feature taxonomy earlier that there is a specific type of feature called an embedding. Now, an embedding is quite a complex. We'll have a quick look at a definition for what an embedding is, but it's quite a complex area. So we're going to say that an embedding takes high dimensional data, so high dimensional vectors, and you can imagine an image here is a high dimensional vector. So an image might have 1 million pixels in it if it's a high definition image, and we'd like to compress the information in that image into a small array of floats. And it might be of length, 50, 200, 100, 300, something like that. So every image in this data set over here, we're going to compress into an array of floats of, let's say, length 300. So why would we do that? Well, one of the reasons we do it is we can do what's called similarity search when we have these array of floats representing each of the images. I could show you, in this case, an image of a hops and say, show me similar images in a database. And your database may have millions of images, and it'll show you, in this case, we can see it's showing you lots of different pictures of hops that it thinks are similar to them. Now, it seems quite magical that it's doing this. Let's dig in a little bit of details how it works. So what the embedding does is it takes our high dimensional image, and the the embedding is converted into this low dimension, so the fixed length array of floats. We're going to learn it. So this means that the embedding algorithm to compute the embedding is actually a learned model. So to train this embedding, what we'll need is, in this case, we'll need, in the image case, we'll need millions of images, each with labels saying what's in them. Then we'll need to train this embedding algorithm by passing in the images with their labels, and we'll get back what's called an embedding model. And with this embedding model, we can take the image and convert it into this low dimensional continuous vector. And remember, a vector is just a list of continuous, meaning numerical values, or discrete numerical values. And that's what our embedding is. It's going to take the high dimensional data. It's going to use a learned model to compress it into this array of floats. And then we can do things like similarity search, but you can also do more with embedding. So on the right hand side, we can see some words, and you actually can do arithmetic on these vectors. So you can take, for example, the word mother, and you can say, well, mother to daughter is a relationship. You can compute this distance, this vector, which represents the distance and the direction from the word mother to daughter in a data set of words. So with this vector here, we could say, I have the word father. What's the equivalent relationship to a father as mother is to daughter? And it will apply this vector, and it will end up at a place and say the closest word we can find matching is son. This is quite magical. You can even do things like say, well, slow to slower gives you slowest. And then you can say, well, I have this word fast, and then apply the same two transformations, and you get faster and fastest. Now, embeddings are used for many different areas. Here we can see we have image processing on the left, and we have natural language processing on the right. And we've looked at applying arithmetic to them and also doing similarity search. But embeddings as themselves can also be used as just simple features in models, in supervised machine learning models. So they're very useful and becoming very widely used. Now, once we have our features available and we want to train a model, the model has an input format that it expects. And some models, for example, deep learning models, expect numeric features as input. Now, what happens if we have a categorical feature? It's a string. What we need to do is we'll need to convert that string into a numeric representation. So we do what's called a transformation. We're going to convert the non-numeric feature into a numeric feature. So for categorical variables, there are encoding algorithms such as one-hot encoding, which will take a string and convert it into effectively an array of ones and zeros, where you have a 1 in the place where the category exists and zeros in all the other places. Now, transformations are also used sometimes to resize your inputs. Your model may expect a numerical feature of a given size, and you have an input that's slightly different size. You'll need to transform that input to match the model input expected, the expected size of the model input. So what else do we use transformations for? So it's not just for data compatibility. We actually use transformations in machine learning to smooth our feature distributions, to make them often to make them follow this normal or Gaussian distribution, because many machine learning models expect data inputs to be smooth and continuous. So for example, gradient descent as an algorithm for training models expects data to be smooth and expects it to form a Gaussian or follow a Gaussian or normal distribution. And if it doesn't work particularly well. If you have lots of outliers like we have in this exponential distribution here, you can see there's some values which are very high, but most of the values are very low, around between 0 and 20. And the model trained with gradient descent won't work particularly well. So what we do typically is we'll take a feature, and this feature here you can see has values ranging between 0 and 2000, and we're going to apply a log transformation function to it. And you can see what it does is it will transform all of the values from the original exponential distribution into a normal distribution, and the values will range now only between 0 and 7.5. So another thing that you want to do in transformations is sometimes scale your values. Often with modeling algorithms that like gradient descent, we'd like values to be scaled within a range between 0 and 1. And mean centered around 0 is often another technique that we use. And that's because, as I said before, You know, some models perform badly if they have numerical features that don't follow this Gaussian distribution, but also you can transform to improve model performance, for example, when you're tokenizing or lowercasing text features. So if you're doing NLP and your model learns about capitalization, it mightn't be very useful. So you want to, you know, lowercase all the text before you start training. You can also use transformations to allow linear models to introduce non-linearities into the feature space. We can do that also with feature crossing that we saw earlier. But transformations are also useful for introducing non-linearities in your feature space. Now, I mentioned that these transformations are very useful for you know, for taking numerical data and normalizing it, or taking categorical features and turning into numerical representation. But not all modeling algorithms require transformations, and in particular, I'll just note the point that tree-based models, so decision trees such as XGBoost, they don't work like gradient descent in the same sense. They don't require a smooth distribution of all the feature values. So you can pass in categorical variables to XGBoost or numerical variables, and it'll just work. But if you are using you know, deep learning, then you'll need to learn a bit about what types of transformations you can apply to your input features to help improve the performance of your models and to ensure that the models actually can train because the input format is correct. So some of the examples are, you know, min-max scaling, so scaling to minimum and maximum values, scaling to the mean and quantiles, Gaussian transformations, logarithmic transformations that we saw earlier, reciprocal, square root, exponential, box cut transformations. And a lot of these are found and used in the scikit machine learning library. And some of the algorithms that require these transformations, and not always, but often, will be popular algorithms like linear regression and logistic regression when you're predicting a numerical value. And you have a linear model. You know, you can still introduce non-linearities through feature crossing, and you may want to transform your data as well to ensure that your linear model can learn the data relationships. And k-nearest neighbors we're going to look at in the first lab, and then we have neural networks, as I mentioned, support vector machines, PCA, and linear discriminant analysis. So if you're going to use some of these techniques, you may think that, okay, I need to transform the data before it's input to these ML algorithms, because otherwise they won't perform particularly well unless the data is, you know, zero meaned and it's scaled to the values are scaled within a range between 0 and 1, and it follows a normal distribution. That's kind of a standard recipe for how to prepare your numerical features for many of these algorithms. Now, here's an example of a transformation, a min-max transformation in Pandas, and this will take a numerical feature and normalize it. So by normalizing it, we mean, you know, squashing the values within a range between 0 and 1. Now, so let's look at the input here. The input is a column called amount. So we can see here that we have amounts ranging from 0 to over 100, and then the y-axis we have the number of amounts that fall in a given bin. So these, you can see here that we have these bins from 0 all the way up to, I think, something like 110. So we're calling the data frame that stores this data df_exp. It's kind of an exponential distribution of values. You can see that, you know, we have a large number of values that are small, and then a smaller number of values that are large. Now, to normalize this particular feature called amount, we can apply the following code. We can get a data frame back called df_norm by subtracting the minimum value from all of the amounts from every row. So for every row, we're going to subtract the minimum value, and then we're going to divide it by the maximum value minus the minimum value. And what you'll end up with is the following distribution of amounts. And we can see they've been squashed into a range between 0 and 1. And you can see that the distribution looks quite similar to the one we had before. So it's not a Gaussian, but we have normalized the values between 0 and 1, and that means there's not going to be big outliers that are gradient based or gradient descent algorithms will, you know, overcompensate for. So it should work quite well with this new input data that's been transformed into the range 0 and 1. So scikit-learn is a very good library with, you know, comprehensive support for different types of transformations, and you'll see some examples in the Pandas intro notebook in our GitHub repo. So now we've prepared the features in our Pandas DataFrames, and we want to start training some models with it. What else do we need to do before we start training the models? Well, typically one of the first things you would do is you would have a training set for your model. So you're going to have some data that you're going to train the model with, and then you're going to keep some data called a holdout set or a test set with some data that you're not going to train the model on. You're only going to use it to evaluate the performance of the model on. So the training set and the test set are pretty standard approaches in machine learning to be able to train your model and then to evaluate its performance on data it has never seen before, unseen data. So what we're trying to do is see if the model generalizes to be able to classify or use regression to predict the values of data in the test set, so in data it hasn't seen before. So we can fit the model in the training data, and that's great, but what we really want to know is, will this model work well on new data it hasn't seen before? Will it be able to generalize that new data? And that's why we introduce training and test sets. Now you can have random splitting of your data, which is a pretty standard way of starting out. You can also have time series based splits, so you might have data from last year for training and then from this year for testing. We'll look at scikit-learn, which is a popular library for splitting your Pandas DataFrames. You can pass as input your data frame of features and your data frame of labels and say, well, I want 20% of the data to be test data in the test set, and what you get back are 4 different data frames. Now the 4 different data frames refer to the train set, and the train set consists of features and labels. So X is our vector of features, and then we have Y. So Y is in fact our it's a scalar. So I'm just going to try to write features here. We've got features, and then Y is our lowercase y is our label. So this is the it's a single value in this case, so it's a scalar, and that's why it's lowercase. And then the other word is test, or train. So test or train refers to the test or train set. So we've got 4 data frames. We've got the features from the train set, we've got the labels from the train set, and then we've got the features from the test set and the labels from the test set. So what we want to do now that we've split up our data, we've randomly split into train test sets, we want to train our model on the train set, evaluate it on the test set, and then iterate to improve the performance of the model over time. Now, in this course, we're not going into too much detail in the modeling parts. We're not going to look at different model architectures. We're not going to look too much at different model algorithms either, and hyperparameter tuning, and many of the different phases that you would go through in improving the performance of your models. There's many good courses out there that you can take to help learn about modeling. But what we're going to do is follow a very simple pattern, which is the following. We're going to get some training data, and we're going to split it up into test and training sets. We're going to define a model that we're going to use to train. We're going to train on the training set. In this case, we're using XGBoost classifier. So we're going to train a classifier. It's classification problem. And we train it by passing in the vector of features and then our data frame containing the labels. So once we've trained our model, we've fitted the data to the model, we can take the test set of features, X test here, and then we can use the model to predict what the output should be, so what the label should be. So y_pred are the predictions that our model has performed on this new test data. If we take the credit card example that we had earlier, we pass in some new credit card transactions, and we get predictions as to whether these transactions are suspected of fraud or not. And if they're not suspected of fraud, great, but we want to know if that's correct. So the way we find out if it's correct is that we can compare, in this case, the labels in the test set, so y_test, with the predictions. And we can get back a classification report here. You can get it back as a dict or in a format that's easier to print out, and this will tell you the performance of your model. You'll be able to compare what good were your predictions compared to the labels in your test set. So we can find, in this case for classification, the accuracy of your model, what percentage of the predictions were correct. We might also care about which ones were incorrect when they were false, which ones were incorrect when they were positive or true, and we can use something called the F1 score to help us balance out how many were false negatives versus false positives in the predictions, because maybe we care more about missing fraud than we do about getting the odd transaction incorrect labeled as fraud when it's in fact not correct, when it wasn't fraud. So this is the general approach we're going to use for modeling in the course, and you're free, of course, to plug in and plug out appropriate modeling algorithms to try and improve the performance of the models that we cover in this course. So if we plug this paradigm for model training into the diagram we had earlier, we can see that the model training stage involves basically fitting the features and the labels from the training data to our model, and then the evaluation involves comparing the predictions made by the model with the labels from our test set. And you want to iterate on this, of course, to improve your models. And typically in machine learning, this is a very iterative phase. You can go back and do exploratory data analysis, try new model architectures, change the hyperparameters. You can tune them to make them better. You can evaluate your models to see if those changes you made perform better, and then go back and repeat and rinse until you've got a model that you're happy with its performance. So model training is slightly out of the scope of this course. There's 10 recommended free ML courses linked here, and you're free to take one if you haven't taken one before. And I strongly would recommend you taking one if you haven't taken one before. But even if you haven't taken any courses, you still will have enough of the basics, hopefully at this stage, to be able to put your first machine learning models in production, build these serverless applications around them, because that's the focus of the course. So we'll move on now to the ML pipelines. ML pipelines are programs that we run in an orchestrated manner. They're going to run on a schedule periodically or maybe on demand. And they're used to create the assets that we have in our machine learning models. So the assets would be the features that we can use to train the models themselves. Let's have a quick look at some of the stages you would find in a machine learning pipeline for computing the features. We can see that we have a number of stages written at the top here. We have collect raw data, process data to create features, store features, and then use the features for training and inference. So this is what we would call a pipeline. It's going to take as input the raw data, and it's going to output features at the end. So the first stage here is collecting the raw data, and this involves finding the data sources, securely connecting to them. They may be different locations. Maybe it's a database, a data warehouse. Maybe you're downloading a file from somewhere. You'll need dependencies to be able to connect to some of those data sources. You might need a connector or a driver. You need to authenticate your client when you're connecting to one of these data sources potentially. You need to know the network endpoint you're connecting to, authentication credentials, an API key. We're going to use API keys in this course to connect to the Hopsworks platform, for example. And that's the basic phrase of collecting the raw data. How are we going to get the data, connect to it, and download it so that we can actually create features with it? So after we've collected our raw data and connected to it, what we need to do is process that raw data. So in a typical data engineering, we call this phase data processing phase. We call it either an ETL stage or an ELT. So ETL basically refers to extracting the data from this raw data, transforming it into the format that we want it to be in, and then loading the data into the target system that we're going to store it in. In data warehousing, we often use the term ELT, which means basically extracting the data from the source data, loading it into a data warehouse, and transforming the data in place in the data warehouse. And we're not going to do ELT in this course because in Python, primarily we do the processing, the creation of features in Python itself. So it's primarily ETL. Some of the things you might need to do in this stage are, clean the data, validate it, make the data usable as features, deduplicate data, pseudo-anonymize data, and then all the feature engineering steps we saw earlier, computing aggregations, compressing data, feature crossing, and so on. Now, once you've computed your features in a traditional machine learning pipeline, you might just store them as training data directly for models. In this course, we're going to do it slightly differently. We're going to use a feature store platform, a serverless feature store, to store these features. And when the features have been stored, then they'll be accessible by downstream clients. That means when we want to train a model, we'll be able to go to this feature store to say, I would like to use these features to create training data for my model. And when you have an operational application that needs features to make predictions, it can go to the feature store as well and say, well, I'd like to look up the the credit card history for this user, the number of payments that have been made in the last month, and I get that feature back and use it as input to my model when I need to make a prediction. The feature store is going to store all these features, and we can use it to do exploratory data analysis to find out what features are there and use those features in our models. So using the features basically means saying, well, selecting features in particular, and I say I'd like to have this feature for, the credit card fraud payment example. I'd like to have the number of payments made in the credit card in the last hour. I'd like to use training data for the last 2 years because on the time before it wasn't that good. So when I'm selecting features, I might need to apply what we call filters, and they could be time-based filters. I want training data over a particular time range, but also could be filters such as, I'm training a model for users only based in the European Union, so I just want the customers based in the European Union. Or you might want to drop some features because they're not allowed to be used in the European Union because of the GDPR regulation. So when you're selecting features for training or for batch predictions, you might get back a big batch of data. And when you're running with an operational system running 24/7, and if we take the credit card fraud example earlier, I have a single credit card payment. I need to classify if it's potentially fraud or not, and I want to look up the features for this credit card holder and for number of recent transactions on the credit card. Well, I can go to the feature store, get those pre-computed features, and use them then in my models. And that's only going to look up individual rows, not big batches of data. So this is an example of an ML pipeline. And in fact, there are several ML pipelines, not just this feature pipeline that we went through here. So the more common one that people will have seen, maybe if you've done a course in machine learning, is what we call the end-to-end ML pipeline. And that's where you go from raw data all the way to a model, and then the evaluation of that model with the predictions that you make. You do it in a single program. And it's great for learning, of course. But in production systems, we often want to split up this pipeline into what we call a feature pipeline, whereas we go from raw data as input and the output will be features. And then we might have another program to go from the features to the trained model. And another program if we're doing batch inference. So batch inference means batch predictions on batches of data. So we might take data that arrived in the last hour or day and make predictions on it. A good example would be Spotify Weekly. So once a week, Spotify will take all of the customers in Spotify, compute a number of recommendations for songs for them to listen to, and then write them back into a feature store where when you log into Spotify, it will give you those recommendations for the week. So it's the songs that it recommends for you to listen to for this week. So the batch inference pipelines are just batch programs. They take the new data. So the new data will be the new features, input features, and it'll produce predictions that will be consumed by some downstream application. I mentioned the online credit card prediction problem. This is what we call an online inference program. And this program will take in, for example, the input features for the new credit card example and predict whether it's suspected of fraud or not. So these are the different pipelines that we have. And we'll go through each one by one. So the first one is the end-to-end ML pipeline. And we have an example that you can see here. We're calling it the monolith ML pipeline. And it's a Python file. And you can see that it goes through a number of stages. You compute the features, you train the model, and you evaluate the model. And it does it all in a single program. And an example would be, Stable Diffusion, if you're familiar with that. You type in some string text, and it will produce an image. And the image looks quite nice. So we have an example of that later on, where I have an iris flower that I compute with a small string saying, give me this iris flower, and it should look yellow. Now, the problem with this end-to-end pipeline is it can quickly grow into a monster. So you might say, well, I like this ML pipeline, but I'm using it to train, but when I want to do inference, I don't need to train. So I'm going to take the same program and I'm going to create two code paths. One is for training and one is for inference or predictions. So this pipeline is really trying to do everything. So I'm going to call it the Swiss Army knife monolithic ML pipeline. So monolithic means it's a big, huge thing that's trying to do everything. And Swiss Army knife, it's trying to do training and inference in the same program. I call this an anti-pattern because it's not a great way to write production code. The code becomes very brittle, and we'll see some of the problems that arise with these monolithic pipelines. But basically, you can have a code path that when new data comes in, it'll create features, make predictions on the model from the features, and it'll have to get the model from model registry, and then output the results. And then when you're training, it'll use the same logic, the same functions to create features. This is great. We won't have any skew between inference and training on the features. But then it'll pass the features to a training function, and the training function will save the model to a model registry. So this will be an external service to model registry. But we have this giant program that's trying to do everything in a single program. Now, the problem with these end-to-end ML pipelines is they're not modular. And by modular, we mean that the different components like feature engineering, model training, and inference are not separate programs. And often they come in a notebook format, which makes it even more difficult to productionize these systems. They're difficult to test. So one of the problems is that if you take the different components, feature engineering, model training, or inference, you'd like to test them individually. I'd like to test each feature to make sure I can depend on that feature. I'd like to evaluate the model and test it to make sure I can depend on the model. Production software needs automated tests to ensure the quality of these assets, features, and models. End-to-end ML pipelines also tightly couple different steps that could run at different cadences or frequencies. So, for example, maybe we have new data arrives every hour, and we compute features every hour. But we only need to do inference every day. We don't need to make predictions once a day. So, and if we took the Spotify weekly example, well, new data or features is coming in all the time, but we're only make predictions once a week. We don't even need to retrain the model every week because, people's maybe music tastes are quite consistent across a few weeks. Maybe they change every season, so we'll retrain it every season. But when we have a giant monolithic end-to-end pipeline, we've tightly coupled all of these different steps. They're going to run in the same program at the same time. And it's hard to reuse features. So if I compute a feature in my feature engineering step, but I have a different model would like to use the same feature, that becomes really hard. You're going to cut and paste that code. And then, of course, if the original code changes and the cut and pasted code changes, they diverge, you have two different implementations of what should be the same feature. And the code for computing these features and the model training, you can't disentangle it. We call these often pipeline jungles. And of course, it's difficult to document the code because it's all in one giant program. So the solution to the end-to-end monolithic pipeline problem is to modularize your pipelines for machine learning. And by modularizing, we mean taking this giant pipeline and breaking up into smaller parts. And we've seen already what they will be: the feature pipeline, the training pipeline, and the inference pipeline. And this involves restructuring your code, refactoring your code, so it's separated into separate functions or classes or modules. And each of those can be easily reused and tested. This doesn't mean you need to abandon notebooks. It means, for example, that for features that are going to be shared across different models, we might move that feature code into Python programs. But those Python programs or Python libraries, we can call the functions from within notebooks. So we can have a notebook that computes features but uses external Python functions from your Python library to compute those features. So you can still have the nice notebook experience, but we get the benefits of modularizing your code because now these functions can be unit tested, and we can run data validation tests across them, and the code can be easily reused because we can check that code into GitHub as a library, we can version it, and it can be reused across many different pipelines. And this enables the code to be easily independently tested and debugging, makes discovery of bugs easier, and also reduces the blast radius of your system. Now, the example here on the left, we can see some water pipes in Google. So in Google data centers, they don't have one giant end-to-end monolithic water pipe feeding all of the different systems. You can see they're color-coded. So if, for example, the yellow pipeline here had a problem, the whole system, the whole data center would not go down because that one pipeline had a problem, which would if we had one monolithic pipeline. The blast radius for that particular problem will be reduced. Maybe some service will be unavailable for a short period of time, but it'll be easier to fix it and easier to identify it because you can see we can follow the yellow pipelines, find the source of the problem, and the problem hopefully isn't as big as redeploying a huge monolithic pipeline. So I mentioned already we have the three different pipelines. We're gonna refactor our end-to-end pipeline into feature, training, and inference pipelines. The feature pipeline is used to create features from historical data, so we call that backfilling of features from some historical data or from new live data. We have a training pipeline which will take the features and produce a model as output, and the inference pipeline which takes new data, unseen data, and produces predictions. So what we can see that unifies these different, go back here. So we can see that unifies these different stages is we have this shared storage layer, the feature and model storage layer. And this is our serverless platform for feature and model storage. And the feature pipelines write to it, and they can run now at their own cadence because they're independent of the training pipeline. The training pipeline can run whenever it's needed, and then the batch inference pipeline will pick up the new features in the model from the shared feature and storage layer to make its predictions. And all of these three programs can now run independently of one another. So when do we run them? Well, feature pipelines often are run on a schedule or whenever new data is available. You can even run them in what we call a streaming fashion, where they run 24/7. Training pipelines are run when we need a new model, often because the old model is stale. So often they're run on demand. And then inference pipelines are run whenever you need to make new predictions on data. So when your application or your downstream client needs these new predictions. Maybe it's on a schedule, once an hour, once a day, or maybe it's continuous 24 hours a day in an online case. So a little bit more on what a feature pipeline is. The feature pipeline is a program that executes a number of steps to convert input data to features. Now, I don't use the term transform, which you often use in data engineering, because that means something else in machine learning. So I'm going to use the word, in this case, the specific words. I want to validate the input data. I want to aggregate it. I like to compress it. I'd like to do binning or crosses. We'll call that extracting features. So these are the specific steps. And the feature pipeline is going to be a program. In our case, it's going to be a Python program. And we can execute these different steps logically as kind of a data flow graph of different feature engineering steps would be one way of modeling it. And you can do that with pandas and frameworks like Hamilton that will execute all these steps as a data flow graph. Or you can just do them, in order in your pandas program. Now the training pipeline will take our features, and you can see here I've introduced something new here. I'm trying to say that these are going to be untransformed input values. So untransformed features. Now by transform, I mean the machine learning transformation that we saw earlier. So, taking an exponential numerical feature and transforming it into a normal distribution. And these type of transformations we do after the feature store, not before, because if we store transformed data in the feature store, it becomes very difficult to reuse those features. And the reason why it becomes difficult to reuse them is because transformations are computed over sets of data. So if I take all of the features, for example, of the amount, if we took the amount feature from our fraud data set earlier, the credit card fraud data set, and if I normalize them, well, what I have to do is read all the values in that table, and I have to divide them by the mean. And when I add new data, the mean will now have changed. And that means I need to reread all the data, full pass of all the data again, recompute all of the new transform values, and this becomes very inefficient. It also means that if I want to create training data, for example, on a time range, I want to have training data from last year and test data from this year, well, that becomes pretty much impossible because the data has been normalized over all of the data. So if you store your data in the feature store untransformed, now these features become reusable because you can pick different training data set ranges, time ranges, and you can also apply different transformations of those features. Maybe someone wants to perform a logarithmic transformation and someone else wants to, a different model needs a different type of transformation. So that's why we have untransformed features as inputs to the training pipeline. The training pipeline itself is a program that's going to take these input features, and it's going to apply a number of steps before we get a model as output. And the typical steps we have, I've mentioned transformations as the first step, but you also have hyperparameters that you would like to set for your modeling algorithm, and maybe you're going to learn them or tune them. Model architecture, maybe it's static, or again, maybe you're going to learn it with some sort of AutoML algorithm. You're going to have to fit your data to the model, that's the training step, and then you need to evaluate your model as well before you're finished. And then when you've a model as output, we're going to use a model registry as a place, a serverless service to store the models that are output from the training pipeline. Now, online models are a little bit different because we've said this already, that online models, they're typically executed by systems that run 24/7. So we might have in a production system, imagine the fraud case, we'll have a stateless application. And this stateless application, what it will do is it will take the credit card payment request, and it's not going to have any historical features. It's not going to know about how many times you've used this credit card or how much money you've spent in the last hour, what your credit history is. It doesn't have any context of whether there's fraud happening at this location or not. So this stateless application can only just take the information available on the credit card itself. So maybe the number, the time, the date, the location, and so on. And that's not typically enough information to make a good prediction of fraud. So what we have is that we have something called a feature store, and I've mentioned it a couple of times. But the feature store is it's this place, this platform that will give us the historical and contextual features as pre-computed features for these online models. So The feature store here will give us the contextual and historical features. We're going to store the feature pipelines, will store them in the feature store, and then the online models can just read them as pre-computed features. So I gave the credit card example already, but if you have an e-commerce web application and you go to checkout and maybe you want to recommend some products when you get to your checkout, the stateless application that's responsible for the shopping cart where you're doing your checkout, it doesn't know your history of interactions with the company. It doesn't know maybe all the session information that's been collected while you've been on the website at the moment. So it doesn't have the history or context. Again, we can go to the feature store to get those features to help make a better prediction of what to recommend to you when you've gotten to the shopping cart stage. So if we put these different components together, the feature store is the service that provides the historical and contextual features in particular for online models. And one of the other benefits of it that we can see here is that when we compute our features in a feature pipeline, and we're pre-computing these features, populating them in the feature store, and then our inference pipeline are using them and our training pipelines are using them, well, we've only computed the features in one place. If instead we had computed the features in the inference pipeline, which is a separate program from the training pipeline, we could have a potential for skew. So different implementations of the feature in the training pipeline, maybe that's done in Python. Inference could even be done in Java. And in this case, when you have a feature store and you've pre-computed the features in the feature pipeline, well, the Java program can just read up the features and they will be the same as the features that were used for training because they're both computed in the same feature pipeline. Now, the online inference pipeline, if we look at it in some detail, the same way we looked at the feature pipeline and the training pipeline, you can say it takes as input. In this case, the input's slightly different. It's an application request, and the application request will arrive at our model deployment. So this is actually a service that we can see here, this model deployment, and it's not a Python program. It's a service that's running. Now, inside the service, we'll typically have some place where we receive the request and we're going to transform the features. So, in this case, we might go to the online feature store, get our features, they'll be transformed as well, and then we'll pass those transformed features on to the model itself. We'll call that the predictor, and the predictor will then make the predictions and output the outputs to a result. And you can possibly have a post-processing step before you return the results to the client. You'll also need the model registry to download the model for this online inference pipeline. Now, if we put these different pipelines together, we get systems for machine learning. And typically we call them analytical machine learning systems. That means a batch machine learning system and operational machine learning systems. This is the online machine learning systems. And we put them together with our different modular pipelines. So the batch system, the analytical machine learning system, this will have a feature pipeline, a training pipeline, and a batch inference pipeline. The batch inference pipeline, the feature pipeline, they'll be run on a schedule. In our case, we're going to look at the iris example in lab 1, where the feature pipeline and the batch inference pipeline are both run on the same schedule. So we're going to run them together. And the training pipeline you need to run then offline yourself in a notebook such as Colab or Jupyter. The feature pipeline will be able to, take historical data and backfill or create features from that historical data. And when it has new data coming in, it can also compute features that it writes to the feature store. So the batch inference pipeline will take the new data, the inference data, download the model, and then make the predictions. The training pipeline will just take the features that arrived with labels for training data, train the models, and write the model back to the Hopsworks platform. And then this is the entire system. This is our analytical ML system. And we've left out the user interface, but in our first example, we're going to have a user interface that consumes these predictions, and it'll get back a graph and some tables. An operational system is slightly different. We can see that the only program that's run on a schedule, the pipeline, is a feature pipeline. The inference pipeline is now an operational service. So it's no longer just we can see it up here in green, the operational services is called model serving. So you'll have typically a model serving infrastructure that will take your model, host it behind a network endpoint so that your application can make requests on that network endpoint and get back predictions. So in this case, in this course, we're going to use Hopsworks. It provides Kserve as a model serving framework. Kserve is pretty much the de facto open source model serving framework for Kubernetes. And what can happen in Kserve is that when the request arrives, we can download pre-computed features from our feature store. And we can also compute on-demand features if we need to from the input feature request. So features that come with the input request. So this is our operational machine learning system. The only other point to note that's slightly different from the batch or analytical ML system is that sometimes we have real-time data that we maybe need features that are very fresh, maybe only a few seconds old. So if you take the example of TikTok, in TikTok when I'm scrolling through my videos, it'll look at the type of videos I'm looking at, maybe it's sport, and within a few swipes or a few seconds, it's going to update the features related to the most recent video types I've looked at, which will be sport. The model won't need to learn anything new, but it can predict that I'm interested in sport because those features have been updated very recently. So in the last module in this course, we look at this real-time machine learning where we can take very low latency, very fresh features and make them available to our online models so that they can really react in real time to what's happening around them in the environment and in the user interactions. The platform we're going to use to store the serverless state in this course is called Hopsworks. It provides both a model registry and the feature store. Let's look a little bit at the feature store in Hopsworks first. So you'll interact with the feature store with your Pandas DataFrames by writing them to the feature store and reading them from the feature store. So it'll act as a place where you can store your Pandas DataFrames and read them as you need them. And typically we'll do feature engineering on the DataFrames before we write them. So aggregations, dimensionality reduction, validations, this is our feature pipeline. And then when we read DataFrames for training, we'll apply the transformations, but also when we read them for inference, we'll need to apply the transformations as well before we feed the input to the models themselves. The actual place where the data frames are stored are what we call feature groups in Hopsworks. These are the tables of features. And when we want to read from the feature store, what we'll typically do is we'll select the features that we want for our model. And we'll say this feature, this feature, this feature. They may come from different feature groups, and we join them together into what we call a feature view. It's not a copy of the data, it's a logical representation of the features we're going to use in this model. And once we've created a feature view, we can then read data frames from that feature view. And that can be what we use called the offline API. So it's going to read large volumes of data potentially for training or for batch inference. But we can also read individual rows or feature vectors for our online models. And that's what we use is called the online API. It's a low latency API for retrieving these feature vectors. So if we're to look at a little bit of code, and what we can see here is that we have the same data frame that we had earlier in the lecture with our credit card payments, and we can create a feature group for that particular data frame. So that in this case the feature group is called credit card transactions, and we have a description of it. We have a version number, so you can have multiple versions of these feature groups. You can have a production pipeline running on number 1, and when you change the features, maybe you want to remove a feature or change the implementation of a feature, you can work with version number 2, and number 1 will keep running that pipeline for the credit card transaction feature group number 1. That can be used in your production system, but in your new version you can try out new modeling algorithms, see if you can get better performance on your model, and then you can switch from version 1 to version 2 when you're happy that the new features are good enough and the new model is good enough. Now, a couple of things that you need to do in your feature group as well. You'll need to identify a primary key. In this case it's the credit card number, and then the event time column. In this case we trans_date time. Once you have the feature group created, in this case we're either retrieving it if it exists, so get or create. If it doesn't exist, we're going to create it. And then once we have the feature group object, we can insert our data frame into that feature group object. This will block until the data frame has been ingested into the platform. So what will happen is it'll write the data frame to the platform, and then a job will be run inside Hopsworks to ingest it into a feature group. So that'll take a little bit of time. You can do that in a blocking manner, wait for the job to finish, which is default, or you can say, well, I'm not going to wait for the job to finish and continue doing your work. The other point to note here, which is very important, is that when we define the feature group, you can see that we haven't defined the columns or the types of the columns. They're defined in the data frame. So when you call insert in the feature group with a data frame for the first time, it's going to take, the feature group will take its schema from the schema of the Pandas data frame that's written to it. So we have defined already the primary key and the event time columns, but we haven't defined any of the other columns in the Pandas data frame. So all of those columns will get written to the feature group, and they'll be created as part of the feature group, and the schema of the feature group will be the same as the schema of the Pandas data frame. Now, when we want to read from the feature store for training data or for batch inference or online inference, we need to create a feature view. So the way we create a feature group is with this, it's a domain specific language for selecting features. It's really just some methods you call on your feature group objects. You say select these features, the amount, location, and fraud from the feature group object, and we'll get back a query object. The query object, you can get a data frame back from it to have it inspect your data and see what it looks like. But often what you'll do is you'll join these features with other feature groups. So you may have features coming from another feature group. We could take the weather example earlier. I'd like to know the weather type when this credit card transaction happened, and I could join in the weather type as a feature into this feature view. Now with the query, this is the set of features, so the set and type of features that I'm going to use to train my model. I supplement it with the labels, so which columns are the labels in this feature view, a description of it, a name for it, and the version. Again, we version these feature views so that we can support multiple versions over time, so that we can do what we call machine learning operations that we'll get into later in the course. Now, when you have a feature view object, you can use it to create training and test data that's randomly split. And in this case, we're doing the same as we did with scikit-learn. We're splitting our data into training and test sets, and we're getting the features in the train set and the test set, and then the labels in the training and test sets. And then you can go and train your models as we did earlier with these Pandas DataFrames. It's also possible to retrieve training data as files. If your data is too large to fit into the Pandas DataFrames in memory, then you would output or save the features as files, and then your programs can read the data from the files to train their models. Now, to complement the state that we're storing in Hopsworks in this serverless platform, we need compute. And the compute we're going to provide for in this course using Github Actions. There are many other platforms you could use for compute for Python. Github has the benefit that most people have accounts, and you've probably seen this button GitHub Actions and are curious about what it is. So the pipelines are basically the Python programs we're going to run. The feature programs, the feature pipeline, the inference pipeline, they're going to run on a schedule. And the training pipelines, we're not going to run in GitHub. We run them on demand in Colab or Jupyter Notebook. And to run these Python programs, the feature pipelines and the inference pipelines, we're going to use something called a GitHub action. Now, the GitHub action basically is what we call a workflow. And the workflow looks something like this. This is a very simple example. Now, this is just pseudocode. This is not the actual YAML defining the workflow. But the action defines a number of steps. And in these steps, we can see that the basic steps in our first lab will be to install Python. We install Ubuntu first, and then Python 3.8. We're going to install libraries defined in the requirements of txt file. We're going to run this workflow at 11 minutes past 11 every day. So using the cron syntax to define that. And then we're going to run a bash script called run-feature-pipeline.sh at 11 minutes past 11 every day. Now, you may wonder why we're running a bash script and not a Python program directly. Well, the reason why is because we're actually going to work with notebooks, at least in the first lab. So the notebooks can be run from a bash script by just using this command here, Jupyter NB convert. So Jupyter NB convert can convert your Python notebook into a Python program, and then it will execute that notebook from the very first cell to the very last cell in order. And so underneath this, the notebook itself will get executed from within this container that GitHub Actions has spawned to run this workflow. So this is basically how GitHub Actions works. It's going to orchestrate and run these programs. You define when to run it. So this time we're running at 11 minutes past 11, not at 4 o'clock in the morning. And we're going to cover this in the first lab. So in the first lab, we're going to cover the iris flower dataset, and we're going to use GitHub Actions to orchestrate these notebook executions. We're going to use Hopsworks to store the features and the models. And, good luck with the lab. It's really important. You're going to get great value out of doing the labs along with the lectures, because, projects and project-based work is how you really get the information, and a lot of information in this first lecture. You want to make it sit. You want to develop your muscle memory for how to restructure your monolithic pipelines into the different feature, training, and inference pipelines, and how you can put them all together into a prediction service that makes your model shine. So go to the GitHub page to look at the code, and you're going to have to fork that repo. Look at lab number 1, and there's homework in lab number 1, so you'll get great benefit out of doing the homework as well. And if you're on a GitHub page, show some love with a star. Thanks, and I'm looking forward to meeting you in the next lecture.